Good afternoon. Welcome to the Safer Sim webinar series. Today we have a presentation from looking at a research project from the University of Wisconsin-Madison. The presenter today is Areen Alsaid. I will turn it over to you. Before I turn it over, I will let people know that we do have a chat box here. So if you do have questions or comments, please feel free to type that into the chat box. Um, we will have time to address those questions at the end of the presentation. So, Areen, I'll turn it over to you.
Thank you, Jacob. Hello, everyone, and thank you so much for joining today. Uh, whoops. Okay. My name is Areen Alsaid, and today I'm going to be presenting the outcomes of our project, our Safer Sim project that I worked on with my advisor, John Lee, from the University of Wisconsin-Madison. Please, if you have any questions, just like Jacob said, put them into the chat box, and I will be able to see them and respond to your questions. Our project is titled A Machine Vision Approach for Estimating Motion Discomfort in Simulators and Self-Driving Vehicles. And as the title suggests, the main objective of our project was to investigate the potential of non-intrusive machine vision-based techniques for estimating motion sickness. Because motion sickness is a real threat to the success of the automated vehicles, but it's also a critical challenge for data collection and driving simulators. Therefore, and in order to achieve this goal, we developed an R-Shiny interactive web application. The main purpose of this application was to help explore the videos. However, we think that this tool is very valuable for video analytics in general, and it will be used in many different contexts. And I will be talking about that in more detail towards the end of the presentation. We also analyzed the driver's facial expressions to examine the correlations between facial changes and motion sickness and their potential to replace other measures of motion sickness. We also looked at the head pose and its correlation with motion sickness. Quick overview of the data that we had. The data was collected in 2011 at the National Advanced Driving Simulator at the University of Iowa. The scenario of the simulated drive included straight and curved road segments as well as traffic circles. And because the combination of traffic circles and curved road segments is a well-known combination to induce motion sickness in simulators, we used that data to look at motion sickness. We had in total 64 participants, but only 48 of those 64 were able to complete the entire experiment and finish the 3 drives, where we had 1 practice and 2 experiment drives. The other 18 participants withdrew from the experiment at some point because of motion sickness, but in our analysis, we included all 64 participants because we were interested in those that got sick as well as those who did not get sick. So overall, our data included monochrome videos where we had 1 video for each drive and simulator sickness questionnaires where we had a questionnaire administered at the end of each drive. The videos and the questionnaire results were both synced by the participant ID. In order to reduce the video to be able to look at the data from the video, we used OpenFace. OpenFace is an open source tool intended for facial landmark detection, head pose estimation, facial action unit recognition, and eye gaze estimation. More specifically, we extracted facial action units, which is a system, a taxonomy for the facial muscle movements, where combinations of action units represent different emotions. This figure right here shows different emotions like happiness, where it's represented by the action units of cheek raiser and lip corner puller, and so on. The other variable that we extracted from the OpenFace output was the head pose, and this included head position and head rotation. That was measured from a camera mounted on the dashboard. Our result, we expected that if facial action units change as a result of the motion sickness, they would change over time, and hence there should be significant correlation between action units intensity and time. However, our results did not show a significant correlation. As we can see here, this is a correlation matrix. Although there was no significant correlations between time and action units, we developed multiple models to try to examine and assess the predictability of simulator sickness scores through changes in facial action units, but none of these models explain the variation in the data. And we believe that this can be due to the combination of the method of data collection and the experimental design presented a challenge in developing motion sickness predictive models from facial action units. Our head pose analysis results showed that the X and Z distance from the camera had a significant effect on the simulator sickness scores. We believe that this is because a result of visually induced motion sickness due to the difference between the design eye point and the actual eye point of the participants. And based on those results, we made a recommendation of careful calibration of participant seating position in order to combat motion sickness. Okay, so as I said, we were expecting that if facial action units change as a result of motion sickness, there will be a correlation between facial action units and time. But this is a correlation matrix, and we can see no correlation basically between time and any of the action units right here. We did still develop different models to assess whether or not action units can predict motion sickness, but none of the models we developed did predict motion sickness basically. And we think that this is because of the combination of the method for data collection, but also the experimental design. They both presented a challenge in developing motion sickness predictive models from facial action units. For our head pose results, we found that the X and Z distance from the camera had an effect on the simulator sickness scores, and we believe that this is a result of visual induced motion sickness because of the difference between the eye point of the design and the eye point of the participant. So we recommend to always have careful calibration of the participant seating position. Okay. Now I'm going to be talking about the development of our interactive web tool. We developed this tool for video exploration purposes as part of this project, but the tool can be used in many more contexts, and we believe it's very useful for advancing machine vision research in general. Because one common challenge that comes with machine learning application is labeling data. So on one hand, you want the data to be labeled by a domain expert, but at the same time, this can be very expensive, very tedious process. So here we developed this tool that leverages semi-supervised learning technique with expert judgment skills to speed the video in this case, or data in general, labeling process. So the process for the tool's development and use consists of 4 main steps. The first step is video reduction, which I already talked about using OpenFace. The second step is dimensionality reduction, followed by an average face estimation and frames coding. And I will talk about each one of these in a bit. For dimensionality reduction is known as an unsupervised machine learning technique where it reduces high dimensional data frames into a few components that capture the most variation in the data. Here in this case, we used a dimensionality reduction technique to reduce the output from OpenFace. The structure relieved by dimensionality reduction techniques provides insight into how machine learning algorithms perform and how similar data points can be classified. But more importantly, they provide a way to visualize the data. So here in our example, in our tool, we used UMAP. It's an algorithm known for its reproducibility, as well as efficiency advantages in comparison to other similar algorithms. UMAP also has an advantage of the ability to use it as a semi-supervised learning algorithm when parts of the data is not labeled or parts of it are labeled. Quick question, can you see my slide right now? It says
Yep, we
the
can.
average face estimation. Okay, cool. All right. So next we estimated an average face to compare the person's, my slides are advancing on their own. Sorry for that. Okay. We estimated an average face to compare the person's facial expressions at a given point to a common, neutral, or what we call an average face. So the way we did that was by calculating the mean of each action unit across the entire video, and then we found the frame that had the closest values to the mean. So here we can see in this example different faces of this participant, but the circled one is what's called an average face. It's kind of more neutral, most common throughout the experiment phase. So this is the dimensionality reduction that I was talking about. This is the UMAP presentation. We're visualizing the first two components right here. And each point on this figure represents one frame from the video. The next step is frames explorations and selection, where the analyst gets to brush and hover over some clusters in the UMAP to look at the associated frames as we can see here. The brushed points are highlighted in red, and these are the associated frame to these UMAP points. All right, so yeah, let's look right here where I'm hovering right now. This is the UMAP space. Again, every point on this frame represents, every point on this plot represents one frame from the video. I can cluster, brush different points, different clusters, and I can see the associated frames right here. So if I look at this clusters over here, I can see the face of the participant being surprised, for example, and this video was recorded for demonstration purposes because of IRB restrictions. So you're gonna see different facial expressions. If I brush the points over here, I'm gonna see the participant happier right here, and so on. I was talking about the cluster size control, where we can allow the analyst to control the size of the brushed cluster right here. I can go bigger to include more points to look at different data points, or I can go like smaller, for example, where nothing is showing basically right now. So the bigger the cluster becomes, the more these frames will start to look less alike. And this is a signal where you should decrease the size of cluster and go ahead and focus on the points that are similar to code them all at once. So once you've decided what your cluster size is, the analyst can come over here, add some labels. For example, I'm looking at the frame right now. It's really happy. I can add happy, add some comments. For example, the participant looks very happy. I can also label arousal and valence, which are two-dimensional dimensions of emotions, and I can hit submit for this. These labels are going to be incorporated with the UMAP semi-supervised learning algorithm. The UMAP space is going to change, and the points that were labeled are going to gray. Now I can select another cluster to look at it again and compare it to the mean face that's showing right here. And you can see the participant is really laughing. Now, looking at the other component of this is the timeline of the experiment. I can select which action unit to show from here. This is showing action unit 1. I can choose action unit 12. This is the lip raiser action unit, and it's typically associated with happiness. So I expect by looking at this, as you can see, the participant is laughing right here, and the action unit 12 intensity here is kind of higher than typical. If I want to look at this very low value of action unit 12, I can use this slider right here to go to that specific portion of the drive, and it's highlighted in blue right here. This is reflective of what part of the drive the participant was in. I can then brush this cluster, and you can see this person has a very serious face, like even below average, and that's why the action unit 12 that's representative of happiness is really low right here. I can add another label, for example, just neutral, let's say, and I can add a comment. The participant looks neutral. and hit submit, and the same process will be repeated again. I think with that, I'd be happy to take any questions.
Thank you, Areen, and thank you for working through those technical difficulties with us. It was great to see what the tool interface looks like. I'm still not, there might have been a little lag when you were working with this tool too, but I think we kind of still get the idea with it. I will add the final report to your project in the chat box for anyone that is looking for more information on the specific project.
Perfect.
And we did get a question that came in during the presentation asking on what you meant by careful calibration for seating position. So if you could maybe describe a little more what that means to carefully calibrate the seating position for the participant.
What we noticed with the X and Z axis is typically when the person was closer to the monitors, to the simulator monitors, motion sickness increased. So we think like carefully considering that when seating participants and uh, changing the design eye point based on the participant's height, because we assume that shorter participants had more difficult time and were more prone to motion sickness because of that mismatch between uh, their eye point and the design eye point. So that's what we meant to ensure that uh, to find some way to get all participants at a seating position that's optimal, basically for that specific design. Also, I will send Jacob my slides in a PDF format, hopefully, so that you can all see it.
Yep, that will be great then. Thank you. I can share that out with all of the registrants we had today. So we do have time for any more questions if there are any others. I'll wait. I'll give people a chance, one last chance to type anything. I will mention that we do have upcoming webinars scheduled for Safer Sim. So we have another one coming up in 2 weeks on April 14th, and that will feature research from the University of Puerto Rico Mayagüez. So keep an eye out for those announcements. And I think that is it for questions. So thanks again, Irene, for kind of working through some of these technical difficulties, and thanks for the presentation. We will circulate that the presentation itself to the registrants here within the next week or so.
Perfect. Thank you so much. Thank you, everyone, for coming.